Alright, this is your example lab for free fall. These are your directions, so you want to describe the motion of an object that's falling that experiences negligible air drag with specific reference to its acceleration. So really you want to find the acceleration of a falling object without air drag. In class, you would take one of your video files. And so here's one of the video files. We have this object in the background. This is your free fall apparatus. What it has at the top there is an electromagnet that's going to be operated by the power supply right there. So you turn the electricity on, and that little part that fell, let me back it up here, or not. There we go. That little part that's falling is metal, so it'll be attracted to the electromagnet at the top. You'll turn the video on, you'll turn the electromagnet off, and the object will fall. That's the apparatus we're using for this particular lab. So now what we need to do is we need to bring that up in Logger Pro. So I'm going to open up Logger Pro, and I'll just do one of these as an example, because typically what we do is we distribute the video work to each person in class. So each person would only have to analyze one video, as opposed to each person analyzing 10. We'll go to Insert, and we'll choose Movie. I have these on my desktop. Let's see, Unit 1, Lab, Video Data, and it doesn't matter which trial. I'm going to pick Trial 6 just for an example. I'm going to play until I see it move. There we go, I saw it move. Back it up. And that'll probably be pretty good. It's not quite up to my white line, but it doesn't really matter. I just need enough points. Well, maybe I'll back it up a little bit more. That looks pretty good. Track using the video, so I'm going to have a meter stick in the background. 1 meter sets my scale. I'm going to set my origin. I'm going to set that up here at the top. And I'm going to turn that off. And then I can set my points. And I'm going to click on that white component that's falling roughly in the middle each time here. Kind of spreads out as I go, but that's fine. I should get some reasonable data there. And then, okay, that looks pretty good. Click over on my graph. Okay, that looks reasonably parabolic. So I'm going to go ahead and choose Y. Click OK. I want a quadratic fit, and click OK. It's not going to give me the greatest number based on the numbers here, but that'll work. This is the graph that I'm going to input into my lab report, so I'm going to go ahead and take a screenshot of this for later. As soon as snipping tool comes up, there we go. I guess if I really wanted this to look nice, why don't I minimize that? I could give this a title. This will be position versus time. Click done, and I really don't need the yellow, what am I talking about? The red. So I'm going to double click here, axis options, and I never use the red, so I'm going to click done, get rid of that. There we go. So now it looks a little nicer, so I can put this in my lab report. Go ahead and highlight. Alright, that looks pretty good. I'm going to file, save as. I'm not sure exactly where I have my file yet, so I'm going to go ahead and save this to my desktop. I'm going to call this graph. And PNG is what I want. I'm going to save that. And what I'm going to do is I'm going to open up Excel. Alright, the important component of this lab was the leading coefficient. What I'm going to need is I'm going to have a trial. Whoops, trial, spell it right. I'm going to have a capital A, and I'm going to have an acceleration. Acceleration will have units of meters per second squared. So to get this squared, I'm going to go right here, and choose superscript 2. Whoops, don't need that part as a superscript. Then uncheck my superscript. There we go. Now I can close my parentheses. There we go. So acceleration in meters per second squared. I'm going to double click between the D and the E to get the column to widen. And usually we do about 10 trials. So rather than type in 1, 2, 3, 4, and so on, I'm just going to type 1 equals 1 plus the cell above. That way it'll increment as I go down. For my acceleration value, it's going to end up being twice whatever value I put in for capital A. And we'll go over why that is in just a little bit here. And so that column I can also fill down. So I'm going to fill both of these together. Since 10 values is what I usually want, I'm going to go ahead and fill it down for 10 values. Now my value I'm going to go ahead and put in there. The first number is the only one that makes sense. That's my A value. That's negative 6.39 and 390. Go ahead and put in all the digits that you have available. Excel may turn that one off, but we can, here we go. What we'll do, since Excel is going to be that way, we're just going to tell it to always place 3 decimal places. That way it won't cut the last one off if it happens to be a 0. And rather than go through 10 different videos for you, I'm just going to make up some numbers. Let's say the next person had negative 5.2, then somebody had negative 4.8. Let's say somebody had, I don't know, we'll just make up a few values here. And maybe I should put a few more decimal places in there. You would get this data from everybody else in class. And so all 10 pieces of data, or however many people we would happen to have in class. We usually want 8 to 10, so we'd have at least that many. And now we want to get an average value, so equal average, parenthesis, and then highlight, close your parentheses, enter. And so we get an average value of 10.769. That looks good. We'll label this as average. And now we'll make our table look nice by giving it some dividers. So we'll go up here to borders, all borders. That looks pretty good. I would say that's fine for the table, so I'm going to go ahead and take a screenshot of that. Looks good. I'm going to call that my table, so file save as table. Let's see, screenshot. I could take a screenshot of my apparatus. Why don't I flip back over here? Let me just open up a video for that. Well, while I'm waiting for the video, I'll go ahead and save. Oh, now it's going to open up. All right, there we go. Screenshot for my sketch of the apparatus. There's my apparatus. That'll work for my apparatus. So I'll save this as sketch. Alright, shouldn't need any more screenshots, don't need this video anymore. I don't need my Excel anymore, but I'm going to go ahead and save that so I can upload that along with this video. Whoops. Oh, got my computer locked up. Alright, if that's going to be like that, I'm going to go ahead and pause here and save those. It's not pause. Okay, now that we have the graph and the table done, we're ready to start filling out the lab activity, or the lab report, I should say. Here's our goal. We want to make sure the goal gets at the top. So what I'm going to do is I'm going to go back to my folder here and open up the, oh, I should rename that. Rename this lab1 free fall. Then I'll open it up in Text Maker. Alright, so this is going to be lab 1. So every lab you do, you'll update this title. Lab 1, and this is free fall. The goal is to describe, let's see, I'll flip back over here. Describe the motion of a falling object. That would be a good enough description there. Equipment we used video. Computer and software, we used free fall apparatus. Variables, since we used video data, our independent variable is time. Our dependent variable is position. And our constant, we could put mass, or we could put location. Either of those two would be fine for this lab. My sketch, I think I called that sketch, so I'll update that file. And I can double check to see that that's what I named it. Go back here and sketch. I need to have the name match exactly in the folder that contains the file that I'm going to compile. Procedures, I need to set up the free fall apparatus. There we go, as shown in the sketch. I need to turn on the electromagnet. And place the falling mass. I need to start the video. Then once I've started the video, turn off the electromagnet. Then, let's see, save graphs. Then I'm going to save the graphs generated. Or rather, this time I'm going to save the video. I'm going to label the video. There we go. And we don't have the angle used. We could just say at the trial number. And we're going to repeat this procedure. Actually, we aren't going to repeat this. Repeat the procedure. We're going to collect data from others in class. Maybe before we do that, we're going to analyze the video. So maybe I should say label the video with trial number. Rather than do that, just label the video with the lab number. That would work better than analyze the video. To obtain an equation fit. There we go. We'll say collect data from others and generate a table. There we go. In the data section, now we want to put our graph in our table. The coding for the inserting these figures is right up here, so I'm going to copy this, Control C, Control V. First one I'm going to place is the graph. And the second one I'm going to place is the table. So make sure that's what I call them. Let's see, I have table and I have graph. Okay, there we go. Now below the graph, I'm going to insert the models. So I have software model. And since I did it in a quadratic the software model is AT squared plus BT plus C is equal to Y. And I'm going to put that in the equation environment. That way it'll square that and the prints will look like equation form. On the next line, so the two slashes will put what I'm going to type next on the following line. I'm going to have A is equal to, and then I'll have B is equal to, and C is equal to. And those numbers will come from my graph. Let's see if I have a nice picture of the graph. Yeah, I can read that pretty well. So negative 6.390. Then I put two lines so it knows it goes to the next location. 19.03. And negative 14.04. That takes care of my software model. I'm going to copy that. I'm going to put in a big skip. Paste it, and I'm going to put in my accepted model. The accepted model is going to be 1/2 t squared, so fraction so that's 1/2 t squared plus v0, so v sub 0, that's how I put in a subscript, plus x sub 0. That'll give me my subscript for x0, v0, and then 1/2, oh whoops, forgot the a. There we go, at squared. For my accepted model, then matching it up with these numbers, I have frac, there we go, 1 tab 2, 1/2, my acceleration. Now since I'm putting in a fraction, I need the equation environment, so I'm going to put everything in dollar signs. And that'll tell me then that the unit that should go here is frac, whoops, meters. I could have just done tab second squared. Oh, put an F there. There we go. So meters per second squared are my units there. Down here, this one is initial velocity, so v sub 0. And so units that'll go here will be frac meters, whoops, meters tab seconds, and then close the equation environment. And the last one, start the equation environment, x sub 0, or initial position. And the unit for that is just meters, and then I'll close the equation environment. Alright, that takes care of my graph. I have the software model that goes with the graph. I have the accepted model that I should have, and I have matched it up with the software model that I received from the equation fit. Below I have my table. Now what I want to list is my precision. So for listing precision, let's see, we don't need that one. Let's take a look at the table. Based upon my table for my, oh, we don't need to open that one up. I could have opened up just the picture. Notice 3 decimal places is what I have. So what I'll list here is 0.001. Okay, I don't need that open. And that would be fine for this precision. I'm going to put in a big skip. Then I'm going to list the qualitative description. Which is the description in words concerning what happened. I'll put 2 lines so it'll go to the next line here. And we could say a mass was released from rest and accelerated straight down. Whoops, there we go. It's just a description in words of what you observed. I think that's it. Let's check, not that one. We will check the, or maybe we won't. There we go. Did I bring, let me get the check off sheet here. It's not there. All right, just a second. All right, got it up now. So this is your lab grading help sheet, point distribution, whatever you want to call it. This is what I'll use to grade all of your labs. As long as you use the template, you'll get all the section titles. You just have to make sure that you correctly identify the variables. And then let's see, the date you don't have to worry about. As long as you use the template, that'll get updated automatically when you compile the file. You'll just have to update the title and update your name. The results section is what we've been putting up, or what we've been working on. So let me move that off to the side here and bring, let's see if I can put those 2, there we go. So qualitative observations, that's what I just put down here, the qualitative description. Now notice I called this results. Here it's called data. Results, data, that doesn't really matter. Data table, I have the table input. We have list of equations used to produce the data table. The only equation I had was I used this fact that 1/2 of A is equal to capital A. An equation that easy, you don't have to worry about listing it. So listing what I have right here, just right there, that would be sufficient for that one, for this particular lab. Graphs, I've got the graph. The equation model, that's the software model that fits, is indicated. We've got that. Calculations, again, the only calculation we had was matching up the accepted model with the software model. So this one, there wasn't much to put in there for calculations. We don't have a force or energy diagram, so in this case the only diagram we really needed was the sketch, which we put up here. And the listing of precision, that's what I listed right there, so 0.001. That takes care of everything we need in the results section. Now we need the discussion section. So the first bullet says to summarize the most important part at the beginning. So basically, was the goal achieved and how do you know? So under discussion, we would say the goal was achieved because we were able to generate a graph and an equation that described the observed motion and offered a prediction of the acceleration observed. Something like that. Because, I mean, you wanted to observe the motion and then make some type of comment about the acceleration. That was the goal. So you achieved the goal. Next part, describe the pattern, principles, relationships that your results show and how they relate to accepted models. So first one, what is the accepted model and justify whether it fits well or not. So another paragraph here. The accepted model was, and then we already have it up here, so just copy it. Don't need the little lines. So Control C, Control V. So the accepted model was this, which is a parabola. When graphed, clearly the graph obtained was parabolic. So there is strong evidence that the model chosen matches the accepted model. Further, we note that the predicted acceleration of, let's see, what we had acceleration from our table, 10.769. Meters per second squared, meters, tab, seconds squared. And now since I'm putting in something from an equation environment, I'm going to put that in dollar signs. So further, we note that the predicted acceleration of such and such, whatever that is, 10.79, is close to the accepted 9.8. Actually, rather than retype that, I'm just going to copy this and put in 9.80. One thing I didn't do that I should do, let me bring that up here, is calculate a percent error. I should have done this on my table before I inserted it, but I'll do this right now once I get it to come up here. So while I'm waiting for that to come up, I'll go back over here, close to the accepted whatever. This yields oops, must be I. A percent error of, and then I'll just put in X's now. Now to put in percent, I'd have to do /%. Otherwise, percent will comment out anything that comes after it. Percent error, which is, and then I'll just put in ... because we'll fill in that in just a little bit. Okay, looks like my Excel finally came up. Or maybe not. Alright, it came up down here. Don't see what's going on. Alright, I'm going to have to pause. Alright, I'm just going to have to leave that as dots. The Excel's kind of locked up at the moment. Let me flip back over. Let's see. Justify the fit. Okay, so then what other models describe the data? Justify any of those fits, so I can go on. Based upon the strong quadratic fit, no other models would better describe the results obtained. That just means nothing else is going to describe this graph better than a parabola. If I tried to do a line, I would miss more of these points than anything else. Okay, let's take a look back here. So justify, that's your justification right there. It's really short. You would only have to elaborate here if there was another model that fit just as well. So if a line was as reasonable a fit as a parabola, you'd have to explain why you chose the parabola over the line. Last bullet in that section says explain how the precision affected your results and justify any explanations. And here we could say precision didn't have much of an effect on the results. And generally the way I describe how to do that is, now if I can get Excel to come back up here. Now it's still locked up. Is if you change the last digit, so like we had accelerations listed to 0.001. Well, if you change the last digit on a couple of those in your table and you get a significant change in your average value, then you could say precision did have an effect. But in this case, we'd say precision did not have much of an effect upon the results. And if I ever get Excel to come back up, I'll add that. If not, I'll leave it at that. Last part, describe your error sources and their effect upon your results. Okay. We could say here the primary error source was the video frame rate. If we had a camera that took more pictures per second, the object would be easier to track. And we could probably track more precisely. Something like that. That's about the only error source you're going to have in this lab. See if Excel, nope, Excel's still not doing anything. Alright, let's go back at the PDF. And then the last bullet is explain how the lab may be improved or what additional research might provide more clarification. Well, in terms of improvement, there's not a lot we can improve besides using a new camera. Or a different camera. I shouldn't say new. Most of us probably had pretty new phones for this. The most significant improvement would be a camera with a faster frame rate. I suppose we could say, and perhaps a tripod for mounting. There we go. That pretty much takes care of your discussion. So if I bring up the result over here, or the requirements over here, what was the accepted model, or let's see, what was the goal achieved? We did that in the first paragraph. Yes, it was achieved. We were able to get a good description. Good description meaning an equation and a graph that describe what went on. Principles and patterns. The accepted model was matched very well. Why? Well, we got a strong parabolic shape. And we got what looks like to be a pretty reasonable percent error. No other models describe this better. If we tried to do a linear fit, it wouldn't be nearly as good, nor would it match the accepted model. Precision didn't have much of an effect upon the results, right? We went out to 3 decimal places, and making a change in that 3rd decimal place isn't really going to affect the average value that we got. Error sources were primarily just the camera. How could we improve? Well, get a faster camera. That's about it. Alright, let me try one more time to see if I can get Excel to come up here. Otherwise, I'm just going to have to compile the video. Alright, I did finally get Excel to come up. So first what I'll do is I'll talk about the percent error. So we'll have accepted negative 9.80, and then we'll do percent error. And percent error is going to be the absolute value of the accepted minus what you obtained divided by the accepted. And let's see, that's percent error, so we actually probably should multiply by 100. And generally we don't want this listed as a negative number, so actually I'll do the absolute value of everything. There we go. And reporting the percent error to that many decimal places is ridiculous, so I'm going to change the number of decimal places. Maybe, there we go. Number decimal places. Now for percent error, I wouldn't go more than 1. So 9.9% error. That's a little higher than we would like. I'm going to save that. Put that in here. Percent error of 9.9%, and we'll say which is higher than we would like. Well, we'll say which is higher than our. We'll say it's our standard of 5% / percent. There we go. But we'll say but still is reasonable based upon, now in my case, based upon making up the numbers. Now if you had actually had real data instead of just making up numbers like I did here, hopefully it would have been better than 9.9%, but if it wasn't, you wouldn't say making up numbers, you'd just say, well, that's what you had, and maybe if you tried again with some different cameras, you might get a better result. But for my specific case, that's what I'm actually going to put based upon making up the data points. And let's see, what was, oh, the precision. Precision did not have much effect. How can I show that? Well, let's say this 4.800, and actually I'm going to copy this. Okay, so Control C, Control V, there we go. That way I have, so this is my original data. Now my last one, let's say I'm going to change a couple of these. So this one's going to be 0.5. And let's say I change this one to, instead of an 8, I'm going to change it to a 2. And let's say the last one, let's say instead of a 2, I have a 9. And let's pick another one. This one, instead of a 0, let's say I have a 0.9. Notice I changed several of those, and it didn't really change my percent error. That's why I'm going to say that precision didn't have much of an effect upon my results. Now, one other thing I could mention about precision, and this would be more for the case, well, actually, this would be another way to think about precision. Let me bring up, let's see, did I save? Yeah, there you go. Bring up the logger profile. Okay, notice for my case, I've chosen all of the points, and I get negative 6.390. If I were to not include that first data point, I get 6.4. If I were to not include my last data point, I already get 6.7. And let's see, let's try bringing this one up a little bit. The bigger the number, the worse I'm going to get. I want something closer to 4. So let me move, oops, keep moving this one back. So in this case, the other way to think about precision is how many of these data points you include. Well, in this case, it didn't really matter too much because no matter what subset that I choose here, I'm not really getting anything close. In fact, I'm actually getting farther away the fewer I choose. I'm not getting anything close to 4. Closer to 4 anyway than what I had. That's the other way to think about precision, is you could say, well, if I just don't include, let's say maybe this one point out here, which I don't already have. Now if I did include that point, notice it completely changes my graph. So I definitely don't want to choose that point. It's one that didn't make any sense. But choosing these points, all of these, it didn't significantly help. And that's the other part that you could put under there. So actually that's maybe what I'll add, the last thing I'll add. Precision did not have much effect upon results because changing the last digit of several acceleration values did not affect the percent error. Nor did choosing fewer points on the graph, fewer points logger pro to create a graph. That would actually be the best thing to say for precision, because most likely if something is going to affect your precision, it will be choosing the points on your graph. Alright, that's a pretty long explanation for the lab, but that is the entire lab. So now let's go ahead and compile. And hopefully it'll compile here in a reasonable amount of time. Oh, that looks like it did. View the PDF. Let's see, it looks like the size here is reasonable. The size here is pretty reasonable. Okay, that looks pretty good. Oh, the one thing I didn't have at output was a name, so let me go back up here. Author. There we go. If you put author in there, recompile. There we go. So then you'll have the title, the name, the date, the goal there, equipment variables, your sketch and or picture in this case, procedure, data, or results, whichever you wanted to call that, your graph, the model that goes with the graph, the accepted model, your data table, your average. I should have put my percent error in there, so why don't I do that just to model this the best way possible. Maybe snipping tool, there we go. Save as table. Okay, that's on my desktop. Let's see, I will go ahead and save that. Desktop looks kind of messy, but that's fine. I'll bring this in here. Yes, I want to replace. Reason I want to replace is because I'm going to recompile now. View the PDF again. And notice now it comes up with my percent error, and I have my accepted value listed. There's your complete example. I'll have it posted. Use this to complete labs 2 through 5.